Okay, last time I made a tutorial making a voronoi partitions using the custom system that I made for the volume. Now this time I'm gonna extend that system so that you can also input the curves or surfaces like geometries and see what happens in doing that. So let's see. For the normal voronoi patterns, what you'll get, for example, if you have like points, random points on a boundary, what you'll get as a voronoi partitions or voronoi pattern is like looking like this. Something like this, yeah. And but let's think, if you have not just a point, but if you have a curve as an input on the boundary, and see if you can get a similar system as a voronoi to get to see what kind of like geometry you'll get as a result. So let's see, these are the inputs that you're gonna input as a curve. What you'll get is something looking like this. The curve that runs in between those curves. Something like this. And the logic is based on the voronoi algorithm, is that each point, first you make a connection like this, which is called Delaunay triangle, and you pick up the middle points of the Delaunay curves, which is on the edge of the voronoi pattern. And if you think the same as for this curve input, you make a connection between curves like these. And you get the middle points. And what you get that connects those middle points is the geometry that you're gonna get with the curve inputted voronoi system. So let's make that thing based on the system that I made last time, so the things that I'm gonna do is pretty much similar to the one I did last time. So let's see how you're gonna do that. So first, let's make empty geometry, go inside and delete this thing, and first of all let's make a boundary, I guess. Let's make a box. Yeah, and also let's make a null and name is color this blue and name it controller to include every parameter that I need in this setup. Let's go to the edit parameter input, and first of all let's set the size for the box boundary. So let's name it size. Let's make a float vector 3 and apply. And the second parameter that I'm gonna set is the thickness of the partition. I mean the voronoi partitions, and maybe the range is between 0 to 1. And let's also set the resolution for the volume, since I'm gonna use the volume for this one. So let's set it to maybe 0 to 200. And last of all, maybe this is it for now. Let's apply, accept, and let's first set the size for the box. The X could be like 0.3, Y could be 1, Z could be 1, and copy this size parameter and paste it into the box, right? So that it looks like a brick wall, the thick wall for now, and convert it into volume using the volume, and use the parameter resolution, could be like 100 for this volume inside a uniform sampling divisions base relative. Okay, and as I did that last time, let's make 2 volumes here. One is for the calculations for the volume, one is to have the property which cells belongs to which ID. I mean the voronoi cells. In this case, it's looks much different than the point-based voronoi. Okay, and let's put a name node here. And make 2 groups. One ID 0 is density, ID 1 is variation, same as before. Okay, now I cannot really see the volume. I think I need to set the resolution a bit smaller. No, maybe not. Let me set the name to density. And the initial value to 1. Alright. Okay. And let's set it to 100. Or I can merely see, but it's there. Alright. And now that I have a volume for the box boundary, let's make a curve that runs inside the box in order to make a voronoi partitions, right? So let's start with the simple line. Okay. And well, the size, the origin, well, I just want to go from bottom to top, so let's copy the Y parameter here, and origin could be minus base parameter divided by 2. Oops. Minus. And the length, the direction is 1 is okay. The length, paste the box size Y again, so that if I change the size here, it will also, the line would also change based on this parameter. Great. And next, let's scale this down a little bit. So that later on I want to make a spiral, so that will match well when I rotate it 90 degrees on the z-axis. So make a transform. Rotate to 90 degrees on the x. And scale it down to 9 divided by 7 divided by 9. Okay. And let's resample this as well to make a lot of points. Could be like 0.2, could be any points, but something like 0.025 should be enough. Also do for the rotated curve. Oh, by the way, I also have to set this length to be matched with the z direction, z parameter here. So copy this parameter and, well, I guess I could multiply this by here. Okay, and let's copy, stamp, and let's copy this line to, well, for this one, let's make like 4 points and copy it right here. I think I should be having x and y the same size, so let's copy this parameter to here. Right. Whoa. Okay, and next, let's use a wrangle to move this vertical line to reshape it like a wave, like these. And let's use the point wrangle. Okay, so let's set the total angle to be pi times 4 and the float size to be 0.2, which will be the size for the wave amplitude, and get all the points for each primitive, which means, oops, just closed it. I'm gonna change it to primitive wrangle, and I'll name it make wave. Okay, flow total angle pi times 4 and the size to be 0.2, and get all the points information from each primitive. And for each primitive, I mean each point, get the point and also get the position of the point. And set the x direction, x position with the size plus using the sine function total angle divided by lengths of the points. Oops. -1 times I, then plus pi. Well, I guess I wanna animate this as well, so pi times number of prim times frame times, I don't know, pi times 2 times 0.01, like it will be like 1.8 degrees, I guess. Okay. And finally, set the point attribute, set the point itself, point position to the new position. Alright, okay, I got the error. What does it say? Okay, seems I'm missing semicolon somewhere, or parentheses. Maybe I don't need this. Alright. Okay. Now supply, if I change this, okay, so if I play this, oh, it's too fast. It's making a wave like this. Okay. That's cool. Now I also want to do the animation on the horizontal side. So what I can do is I can rotate using transform. And to the using the X direction, X axis. And merge. Okay, and if I play it, yeah, somehow it's not touching. I think it's not moving as I expected. The first one should also move. So I think I'm missing something here. Maybe okay. Should plus this. Now it's moving as I expected. Okay, so now I have 4 curves on horizontal position, on 4 curves on vertical positions like this, and each curves is making like a sine wave animation, and somehow it's making in between those curves you'll be having a voronoi wall like I showed in the sketch. Now let's try to make that effect. Now let's try to make that geometry using the volume system, volume based system. Okay. Now let's look at the geometry spreadsheet and look at the primitives. Just to make sure, let's make primitive wrangle. And for each primitives, set the ID to primnum. Like this. Okay, now I have those two together. Let's use wrangle to communicate to each other. And this time I'm using a volume wrangle. And for the first input, it's come from here. This is the volume, and the second one from the based input curve. Now, the code I'm gonna write here is pretty much similar to what I wrote last time. First, you set the variation and min distance, something really big as the initial number, and for each primitives, and primitives on the second input, Now, first thing first, I'm gonna get the minimum position, which is minimum position between the point on the volume and the each primitive curves. Now the minpos, I'm gonna use the minpos function in the vex, and I'm gonna use a filter here. If the ID is equal to I, and vector direction to be point position minus minimum position. And I've just found the spell mistake. And the distance will be length of direction, and if the distance is less than minimum distance, then feed back the minimum distance with the distance, and the variation will be I. And on the end, you'll have the least shortest distance with the the information that the point X belongs to which ID, which variation for the voronoi cell. And let's feed back the variation using the variation, and the density to minimum distance. Okay, and apply. Accept. Let's look at the this itself is already making some interesting visuals. Let's look at the geometry spreadsheet. Well, now you have two volumes. One is density and second was variation. The variation has the information for the ID that which point belongs to which cells, and the density have the information of the minimum distance between the curves compared with the curves relative to the curves that I mean. Now let's do the second wrangle this time. A volume wrangle again, but let's name this volume feed ID, and let's make a second volume wrangle. Okay, now let's set the density to 0 first, so I didn't need it to input any number here. And float, let's set the thickness. Let's get the variable thickness from the parameter controller that I set it before. And let's set the resolution to 2, which this resolution means the resolution of the volume partitions, the voronoi partitions. Now let's make a for loop. Use the resolution to iterate 3 times. And this 3rd time. Okay. And make the direction vector set to int, and direction, let's normalize it to make it like a sphere shape. So more resolution you have, more spherical vectors you'll get. And make a neighbor position. The point position itself, the point position of the volume plus the direction times the thickness. This means that the now think that this is a volume, and for each voxel seeks for the different ID. Now this let's assume that this voxels belongs to ID 1 and there's a volume ID 2, in this case variation. And if the voxel finds another variations within the search area, then make this voxels to be a part of the partitions. Like this. Something like this. So let's do that. Okay. To normalize the direction here. And vector size comes from the CHV controller size. Right, and let's filter the neighbor position using the size, because if it's too big you won't be able to find next ID variation if it's outside a box. So I'll do this for each X, Y, and Z using the max and the min. Size X times 5.5 minus thickness, and size x times 0.5 minus thickness. Okay. And copy this for y. And z. Okay, and finally you'll have neighbor variation from the volume sample from the neighbor position, right? If the variation is not neighbor variation, which means the variation itself is different with the next door variation, then set the density to 1, right? Now let's just get the density and get rid of the variation volume at this point. So let's use the delete. The name, density, delete non-selected. Okay, and I think I don't see anything which means I think I'm not doing correctly somehow. Let's try convert VDB and VDB convert fog to SDF, and yeah, I don't see anything, so I think I get something wrong somewhere. Let's check from here. Now, okay. Yeah, I'm looking at the end primitives one. Minimum position, distance. Okay, let me try. Copy this. Paste it here. And okay, well, I think this one is doing okay, I believe. Yeah, and the next one. Wait, what's this? Oh, wait a minute. Why am I not having anything here? So I'm deleting not. I have density name. Okay, I have a name density here. Oh yeah, I have it. Okay. Seems I have it. Now let's set the fog volume to be 0.1. Think it's not enough resolution or something. Let's see. The volume. What was the resolution? Well, it was 100, so I thought it was enough. Oh yeah, the problem with is the thickness, because it's 0. Okay, let's set the thickness somewhere like 0.015 or something. And I can merely see it. But if I... Okay. Now I have it. And it looks great. And let's do some smooths. BDB smooths. SDF. And convert to BDP. Convert to polygon. And voila. And now you can animate this like this. Let's make it to 100. And cache this. And let's play this. And yeah, looks awesome. And that's it. Let's make a flipbook. Play. And you'll be having this coiled animated wall based on the curve inputted voronoi system. Okay, that's it. Thank you.